I want to tell you about something that just happened with this interstellar comet, and honestly, it's making a lot of people nervous. So NASA just noticed a fresh change in this object called 3I Atlas today, and they quietly pushed an update to the official solution. And what that update tells us is that this thing is still not behaving the way it's supposed to. Before we continue, if this has your attention, you can subscribe, turn on notifications, and hit like anytime. And for the best viewing, switch to full screen and enjoy what's coming next. On paper, we should be in the boring part of the story by now. The comet has passed its closest point to the sun. It's heading outbound. The energy is dropping. Everything about it should be slowing down, calming down, becoming more predictable. Instead, the latest update says the opposite. 3I Atlas has changed again, and if you've been following this interstellar visitor with me, you know that every time it changes, we learn something new, something unexpected. And this time might be one of the clearest signs yet that this thing is still in active evolution. It's still doing stuff. It's not settling down. So let me walk you through what happened, because this is actually pretty fascinating when you break it down piece by piece. Every day or so, NASA and a bunch of observatories around the world feed all the newest measurements of 3I Atlas into an orbit solver. It's basically the sophisticated piece of software that takes all the data and tries to make sense of it. You give it where the comet was in the sky, exactly when you saw it there, and how all the previous forces that we know about should have moved it: gravity from the sun, gravity from the planets, all of that. And the software crunches all those numbers and spits out an updated prediction. It tells you where the comet should be next, where to point your telescopes tomorrow, where to look next week. As long as the model is good, as long as we understand what's happening, the differences between the prediction and reality stay small and random. Those differences are called residuals. Think of them like the margin of error. When everything's working right, those residuals just kind of bounce around randomly. Sometimes the comet is a tiny bit ahead of where you thought, sometimes a tiny bit behind, sometimes a little to the left, sometimes a little to the right. But it all averages out. Today, they weren't random. When the newest data points went in, when they plugged in where they actually saw the comet in the last 24 hours, those measurements didn't scatter around the old solution the way they should have. They leaned every fresh position. Measurements sat a little bit off to the same side. It was like the comet had quietly drifted across its track again since the last update. That's your first clue that something changed. The fresh change is literally baked into the new orbit. The numbers themselves are screaming that something is different now compared to yesterday. To bring the residuals back down. To make the model fit reality again, the team had to tweak the non-terms. That's the part of the equation that accounts for jets of gas and dust, giving the comet tiny rocket pushes. Because comets aren't just dead rocks floating through space. They're active. They're venting material. And when that material shoots out in one direction, it pushes the comet in the other direction. It's basic physics, action and reaction. Yesterday's solution assumed a certain strength and direction for that push. The team had calculated how much thrust the comet was getting from its jets and in which direction that thrust was pointing. Today's solution needs a different one. The updated fit says 3I Atlas is now experiencing a slightly stronger sideways acceleration than before. Not catastrophic, not like it's suddenly going to veer off course and come screaming toward Earth or anything dramatic like that, but absolutely real. Measurable, significant. The comet is pushing itself in a different direction now than it was yesterday. Something about its activity pattern has shifted. Now, while the orbit people were wrestling with that, trying to figure out what the numbers were telling them, the imaging team was doing their own comparison. And this is where it gets really interesting, because they were seeing the same story from a completely different angle. They stacked yesterday's deep explosions all, the images they took over several hours to get as much light as possible. Then they stacked today's images the same way. Same instrument, same filters, same tracking, everything identical except for the time. And then they blinked between them, just flipped back and forth. Yesterday, today, yesterday, today. Watching. 4 differences. The overall outline looks familiar. You've got the bright inner coma, that glowing cloud of gas and dust right around the nucleus. You've got the extended tail stretching away from the sun. The structures and patterns are broadly the same, but when you look closely at the region right around the nucleus itself, you see the second part of the story. The bright core is no longer sitting comfortably in the middle of its own glow. In yesterday's data, the inner coma had a slightly flattened shape, kind of like an oval, with the core nestled along the central ridge. The brightest point was right where you'd expect it to be, centered nicely. In today's stack, that ridge has thickened on one side and thinned on the other, and the brightness peak has slid noticeably toward the thick side. It's like someone grabbed the whole inner coma and tugged it a bit to one side. The coma hasn't just brightened or dimmed uniformly. It's redistributed. The material's coming out differently. now more heavily from one side, less from another. And on top of that, there's something else. A faint secondary streamer is now visible, coming off at a different angle than the main tail. It's subtle. If you just glance at the image, you might not even notice it. But once you enhance the contrast, once you really dig into the data, it's clearly there. A fresh thread of material feeding into space from a spot that was quiet before, or at least much weaker in the previous frame. So now we've got two separate hints pointing at the same conclusion. The math says there's a new sideways push. The orbit solution had to change because the forces on the comet changed. The images say the inner coma is heavier on one side now, with what looks like a new or stringent jet-pumping material out into space. Those two pieces of evidence are completely independent different teams. Different techniques, different data, but they're telling the same story. And then there's the light curve. This is the third piece of the puzzle. As always, the teams measured how the brightness of the comet changes as it rotates, because these things spin, right? And as they spin, different parts of the surface point toward us. If one side is more active than another, if one region is venting more gas and dust, then you'll see the comet get brighter when that active region faces you, and dimmer when it's pointing away. Yesterday's curve had a repeating pattern that matched a slightly sped-up rotation period that they've been tracking for days. One main peak in the brightness, one smaller bump, a bit messy, but familiar. The kind of light curve you'd expect from a comet with one dominant active region, and maybe one or two smaller ones, today. When they folded the new brightness data over that same rotation period, the pattern didn't line up anymore. The main peak has shifted in phase by a little bit. It's arriving earlier or later in the rotation than it should. And the smaller bump has grown into something nearly equal in height. So now it looks more like a double peak per rotation, instead of big peak, little peak. That's what you get when a second active region suddenly becomes just as important as the first one. Or when a new vent opens up and starts contributing regularly to the brightness. Two strong sources of activity mean two strong brightness peaks as the comet spins, and each one faces us in turn. So, put all of this together. Look at the complete picture. The official orbit had to be updated, because the comet moved slightly sideways relative to where it should have been. The inner coma is now visibly lopsided, with a thicker side and a new streamer that wasn't there before, or wasn't nearly as strong. The rotation signature shows two strong brightness sources instead of one dominant and one weak. That's the fresh change NASA noticed today. It's not a single dramatic explosion. It's not like the comet suddenly split in half or flared up 10 times brighter. It's a quiet reconfiguration. The comet has updated itself. It's changed its internal configuration, and we're seeing the effects of that change in multiple independent ways. So, what's actually going on physically? What's happening inside this thing to cause all of this? Inside 3I Atlas, the heat from its dive past the sun is still migrating inward. And this is slow physics. This isn't something that happens instantly. The outer crust responded first because it's the first thing that got hit by all that solar radiation. It started venting the easy ices, the volatile materials that sublimate at relatively low temperatures. It started shedding loose dust. But now that wave of energy is reaching deeper layers that have different compositions, different mixtures of ice and rock and organic compounds, different fracture networks, different structural weaknesses. When those deeper pockets hit their threshold temperature, when they finally get hot enough to start sublimating, they don't necessarily vent from the same spots as before. A new crack opens somewhere else on the surface. Maybe there was a weak spot there all along, and now the pressure from below is finally high enough to force it open. An older stressed fracture widens. Maybe it was already open a little bit, already venting a small amount, but now it gets bigger and starts pumping out way more material. Gas finds an easier escape route out of a different face of the nucleus. Maybe the old pathways are getting clogged with dust, and the gas carves a new channel through a different part of the structure. That instantly changes which parts of the comet are active and how strong those regions are. The whole pattern of activity shifts. From the outside, looking through our telescopes, it looks like a shifted brightness peak in the coma. It looks like a new streamer feeding the tail. It shows up as a different thrust direction in the orbit solution, and it creates a double-peaked light curve as the comet spins around. In other words, the internal plumbing just updated. The comet's venting system reconfigured itself. What was a strong jet yesterday might be weaker today. What was barely active yesterday might be roaring today. The whole flow pattern changed. And here's the important thing. This kind of change doesn't just rewrite the pretty pictures. It doesn't just make for interesting images and puzzling data. It rewrites the forces on the nucleus, too. Strong, active regions on different sides of the comet mean different torques being applied as the thing rotates. Every time an active region faces the sun and really starts pumping out material, that creates thrust. That thrust tries to spin the comet up or slow it down, depending on where that jet is located and which way it's pointing. That can tweak the spin rate, make it rotate faster or slower. It can tilt the spin axis, change which parts of the surface get heated most intensely by the sun, and that changes how future heating hits the surface, which changes where future activity happens, which changes the forces. Again, it's all connected. It's all feeding back on itself. The longer this goes on, the more strain builds up inside a body that was already under enormous stress from its passage through the inner solar system. This thing came screaming in from interstellar space, dove close to the sun, got absolutely hammered with heat and radiation, and is now trying to adjust to all of that. If the activity stabilizes in this new configuration, if these two dominant vents keep running at their current strength and nothing more dramatic happens, then 3I Atlas might ride this phase out. It'll spin a little faster. Maybe the spin axis might presses a bit, but it'll slowly fade as the deeper layers run out of volatile material and the energy dissipates. But if instead we see more fresh changes like this, if every few days there's a new vent opening, new shifts in the thrust direction, new drifts in the spin state, then we're watching a nucleus that's constantly rebalancing itself under stress. It's like a building with cracks spreading through the foundation. Every time one crack stabilizes, another one opens somewhere else. And history with other comets tells us there's a limit to how many updates a fragile body can handle before something breaks for real. We've seen comets fragment, we've seen them split into pieces. We've watched nuclei that were stressed by repeated close approaches to the sun just come apart. It usually starts with exactly this kind of thing: changes in activity, new jets opening, shifts in the rotation, the nucleus trying to cope with forces it wasn't built to handle. Sometimes they make it through, sometimes they don't. Right now, NASA's language stays careful. You read the official updates and they say things like updated non-gravitational parameters, evolving inner coma morphology, evidence for changing activity distribution. Very technical, very precise, very neutral. Underneath all that careful language, the simple summary is this: 3I Atlas just changed again. The models had to be updated because reality didn't match what we predicted. The pictures had to be reinterpreted because what we're seeing now is different from what we saw yesterday. The story is still moving. This thing is still evolving. And that matters because this is an interstellar object. It didn't form here in our solar system. It came from somewhere else. It formed around a different star. It spent who knows how long drifting through the cold darkness of interstellar space. We've only ever seen a handful of these things, and getting to watch one go through its close approach to the sun, getting to see how it responds to that experience in real time, that's incredibly valuable scientifically. Every change tells us something about what it's made of, how it's put together, what conditions it formed under. But beyond the science, there's just something captivating about watching this thing continue to surprise us. Every time we think we've got it figured out, every time it seems like it should be settling into predictable behavior, it throws us another curveball. So, if you want to see whether today's fresh change is the last big adjustment before this interstellar visitor finally calms down, or if it's just one more step in a chain of updates that ends with something more dramatic, you're going to want to keep watching this with me, because right now, we're in that moment where it could go either way. It could stabilize. These two active regions could keep chugging along steadily, slowly weakening as the comet moves farther from the sun and cools down, and eventually we'd just be left watching it fade into the distance. Or, we could wake up tomorrow and find out there's been another fresh change, another shift in the activity, another new jet, another update to the orbit, another reconfiguration of the internal structure. And each time that happens, each time the comet updates itself again, the question becomes a little more urgent. How much more can this thing take? How many times can it reconfigure before something gives way? We don't know yet. Nobody knows. We're watching it happen in real time, day by day, measurement by measurement. That's where we are right now. That's the story of today's update. NASA noticed a fresh change. They updated the solution. The images show it. The light curve shows it. The orbit shows it. 3I Atlas changed again. And we're all watching to see what happens next.